Hello, welcome back to our channel, and we continue our discussion about the oscillation and the circuit called as oscillator. So we saw in our previous module, oscillator is a circuit or a system that produces a waveform at a single frequency, omega. Okay, so that signal frequency waveform could be a sinusoidal, could be a square wave, or could be a triangular wave or sawtooth wave, or the period of pulses. And we saw that we basically have a gain block, for example, in an amplifier, and to the amplifier we have this input, we have an output, and then we feed back that output through another block called as feedback network, and then feed the output of the feedback network back to the amplifier. And we see that if the output signal we feed back to the amplifier's input is out of phase, so there is a phase difference between the input and the feedback signal, the feedback is said to be negative. However, if the signal that we feed back and mixed with the input of the amplifier is in phase, so input and the feedback signal are in phase with each other. It means we have the positive feedback, and that kind of feedback generates a sustained oscillation at the output. So we saw that we have this amplifier block and we have this feedback network, and we remove the external input from the system. Rather, we just connect the feedback's output directly to the amplifier, the input. So this is a circuit of or a system block diagram for an oscillator where we don't have an external input. Rather, when you switch on the DC power supply, you basically have a noise into the circuit. That noise uh, gets traveled through the loop, and the feedback network acts as a filter, picking up or filtering up a single frequency of a signal determined by the network of components that you use to build the feedback network. And by filtering that only single frequency, you get go to the amplifier, which amplifies that signal frequency. And again, the cycle process repeats throughout the loop that produces your sinusoidal or square or triangular, depends on whether it is a linear oscillator or non-linear oscillator. In case of a linear or harmonic oscillator, you will have a sinusoidal block. So there are mathematical conditions to express the condition when the oscillation will start and when it will not. So the condition is that you have the feedback gain. Rather, it this is also called as an attenuator block actually. So why it is called as attenuator and this is a gain block? Because it you feed the signal and it actually attenuates the signal amplitude, right? Out of the many frequency signal, it just picks up signal at the single frequency and then feed it back. And this is a gain block which amplifies your signal. So the first condition, your beta has to be less than 1. So imagine you have, let's say, beta is equal to 0.1 and the gain of the amplifier is 10, then you can say A times beta is equal to 10 multiplied by 0.1. It is about, it is 1, right? 10 into zero point 0.1. And then you can say that for if this condition is met, your oscillation can start. So usually you make sure that your A times beta is greater than or equal to 1. Okay, so the oscillation starts actually when your A times beta is greater than 1. So this is actually a loop gain. And that loop gain you calculate by breaking up the loop somewhere. For example, I have opened the loop here. So you got this VO, and then there is an input to the feedback. So VI is essentially your VO actually. Okay, so you can write also the expression, but before that, let me tell you. So your oscillation will start when AB is greater than 1, and your oscillation will then get stabilized when your loop gain decreases and settles at A beta equals to 1. So you have a kind of this kind of signal, for example, for the oscillation. You start like this and you have a slowly increasing oscillation, and then you have a sustained period, and then you have a stabilization there. Okay, so this period is basically AB times AB is equal to 1, and here is A beta is equal to 1. So that's how it gets there, right? And now you can write some expression here by when you break the loop here, you actually can see that your VO is equal to A times VF, and VF is beta times VO. So you can write actually VO is equal to A times beta into VO, and then you actually can say that VO over VO equal to A times beta, or A times beta is equal to 1. And that's what we are saying that. Okay, so you have to make sure that your oscillations are sustained. Now, uh, there is a when you have a signal. For example, it is a linear oscillator or harmonic oscillator, and it produces a sine wave at a single frequency, let's say omega is equal to 2 pi f. So that frequency of oscillation you want to have, so you have to satisfy the Barkhausen criteria. So the first condition I just explained to you, for that says the magnitude of the gain around the loop, so that is A beta, is must be equal to unity, greater than equal to 1. Okay, so when that is happening, you are sure that oscillation is likely to happen. Second condition is that your phase shift around the loop, when your signal travels into the loop, around the loop, at this frequency omega naught, must be exactly 0 degree, or it is also called as multiple of 2 pi radians, that is 360 degree. So when you have these two conditions made, you can say that you satisfy the Barkhausen criteria, and you have a frequency of oscillation at the desired value, and that value is determined by the components you have used in the feedback network. Okay, so hope you understood the concept of condition for oscillation, how it is required, and what conditions, and how to satisfy that. So if you like this video, click the like button, subscribe to the channel, share it with the others for a wider reach, and stay tuned for more informative contents like this. Till then, wish you happy learning.